Nice to see you all again. I hope you've had a first good evening, maybe reading some of the notes that you have, and sorry for the volume of them. I hope you read them all in great detail. We'll be needing all of the information right now. No, this is more for, some of it is more for background reading, appendices in particular. But the two chapters in gauge theory I think you might find useful, also later when you leave. There will be more notes coming today, less notes when we start dealing with higher order diagrams, with loop diagrams, and then there will be more notes later, but usually all a little less pages than what you got yesterday. Also hope that the problems were reasonably doable. Excuse me for the minus sign confusion regarding this covariant translation, but I think everyone got the answer in the end. If you take the passive point of view, when you consider a physical point not moving, you just change the coordinates around it. That is the point of view. What I'd like to do today is round off the discussion on the general aspects of non-abelian gauge theory, the building of the Lagrangian. I've been very general so far with SUN. I'd like to make it a bit concrete by looking at SU2. That's not QCD, that's actually the original Yang-Mills theory. Discuss a little bit global symmetries of the QCD Lagrangian, and then go to Feynman diagrams, Feynman rules, and start looking at actual collision processes. And at various stages during the lectures also the particle model will come back in, because it is at the heart of describing collisions at the LHC. But of course in time also the particle model in the context of having an interacting theory like QCD, rather than like a free theory that Feynman thought of. So let me begin with the stage where we were yesterday. We had seen that actually building a non-abelian gauge theory is not difficult at all if you know the how to construct covariant derivative. Once you have that, you know how to construct fields that transform nicely, and then you just put things together. So we have the nagged non-abelian gauge theory can be written in this so-called Lie algebra valued form as follows. Well, already appealing, of course, to your skills and thinking a bit abstractly, because all of these objects are multi-components. This is an n-component spinner. Each component is a 4-component spinner. This is a row version of that. And this was this field strength tensor, which had a commutator in one of the fields. So this is a beautiful form, nice for slides and t-shirts, but if you like to work with it, we should maybe also have a way of going a bit more to express more detailed form in terms of the components. But before doing that, let me just discuss a little bit the issue of what would this be like for SU2. Then we know everything more or less, so so let's take up the particular case of SU2 just to make it a bit insightful what this looks like. I know from experience in classes I teach in the Netherlands that sometimes that can be helpful. It could well be that you are well beyond this, I suspect a little bit, but I'll assume that this will be useful for you too. So, yeah, if you look particularly at the interaction term, in here, then that looks like a G psi bar W slash psi, right, in the very general form. But we can write this out as G psi bar gamma mu W mu A T A psi. Right, I've done two rewritings. I've written gamma W slash, made the gamma mu explicit, and also made the Lie algebra valued form explicit. Right? And then it may be even useful to write this with all the indices, at least for once. And I'll only use the group indices for now. Right? So I'll put little I here for the group index. I'll go over it again in a moment. Gamma mu, W mu A, T A I J. So I runs from 1 to 2, this is SU2, and J also. You see here, this is a contraction over 3 generators. And, well, you just have I, J, J. If you wish, I'll do this briefly, and just to remind you, if you also want to write down spinor indices, if you haven't seen this before, remember this is a, should I do this? Maybe useful? And then you can forget it again. This is a spinor index, labeling for each of these 2 fermions, the 4 components of the spinor. This thing has index alpha beta, spinor index alpha beta. This is not a spinor, this is not a spinor, and this has index beta. Right? So looking like this, it certainly doesn't look like a particularly nice and elegant form. But if you know a bit the background, you see that it actually has a very nice structure once you phrase it in terms of Lie algebra valued fields. So the original thought of Yang and Mills, when they built this theory for the first time, they didn't do it as we did it, they did it more through an inductive procedure, was to think not of quarks. This is in 54, there was no such thing as a quark even in the minds of anyone. So they thought the proton and the neutron would be a nice iso doublet of spin. So not like real spin, but like spin, iso spin. And to build it, and they were anyway very close in mass. So what this term tells you, for instance, that all these n components all have the same mass. Right? If, by the way, if each of these components had a different mass, there would be no invariant symmetry. Right? Then the SUN symmetry demands that they all have the same mass. But they tried to build it anyway and say, well, the difference is a small effect. But it didn't quite work out in nature that way. But it certainly was a beautiful result. So for SU2, the TAs are 1/2 I sigma A, the Pauli matrices. Why did I have the I here again? I made the choice of having them anti-Hermitian. And then no I, the exponent for the group element. So, for example, in that language, W mu of X, the Lie algebra valued form, would be 1/2 I times W3 mu W1 minus I W2 mu W1 mu plus I W2 mu minus W3 mu. So this is just an explicit way of writing the Lie algebra valued form, just because I know this Pauli matrices by heart, as no doubt you do as well. The lambda matrices I don't, but it will be something similar. This is anyway good to do if you look at Lagrangian theory. There is an SU2 non-abelian gauge theory in standard model, and these are W fields. So that's for the gauge field. The covariant derivative then looks like d mu on psi will be d mu. Let's call the 2 components in honor of Yang and Mills psi n and psi p and psi n, just as a label. Minus g, and then here W3, W1 minus I over 2, W2, W1 plus I, W2 minus W3, psi p, psi n. Oh, I dropped the mu's here, but never mind. You can add them in. So you see that the covariant derivative here just takes the derivative and here mixes things up. It mixes the two components. Now, if you do QCD, I mean, it's anyway a bit of a abstract and hidden quantum number that gets mixed up, this color quantum number. But for SU2, for the standard model, this is identity mixing. You're mixing electrons and neutrinos, or you're mixing up and down quarks. So their non-abelian gauge theory has a bit of a more real feel to it. It mixes things in identity space. That's really a very beautiful aspect of non-abelian gauge theory. So that's for the covariant derivative on the field and the defining representation. For the adjoint representation, you can write this, right? And then what is the G mu as a component? Well, it's not so difficult to work out. This is equal to d mu w mu a minus d mu w mu a plus g epsilon a b c w mu b w mu c. Of course, the epsilon is very typical for SU2. Can anyone tell me if I would is there any other group that would have the same field strength tensor? SO3, right, has the same structure constants. Very good. So, but certainly having this picture in mind to see what a Lie algebra valued field really looks like in components can be useful sometimes. Okay, so this gives a bit of a concrete maybe look at what the general non-abelian gauge theory looks like. We discussed also yesterday the different possibilities of constructing such terms. So let's just now go to actually constructing the oh, I should do one more thing. Go back into the more general case and look at the components. So general case. And then let's light this Lagrangian out in terms of components. And particularly for this bit. We call this the LG squared term. So the LG squared term I can write as is a trace, and this will be contracted A TA, B TB. So no surprise, I will get here trace TA and TB. That's the only object to take a trace over in color space. And then here are the various terms: a quarter, d mu a minus d mu a, d mu w mu b minus d mu w mu b. Those are the quadratic terms in the action. And then we have minus g f c d a. I'll move out of the way in just a second. D mu on w mu b plus w to the fourth term. So all of that in the g squared term. This is a bit trivial here. Here already I've used the commutator relation. You see a structure constant theory. You see here three W fields, but one has a derivative. And I think one of the problems we'll assign today is to see if you can derive the Feynman rule from this term. We'll get to that also in just a second. But that's just written out now. It's important when you have a Lagrangian and you look at the kinetic term that it has the right sign. So you want, in the end, if you have, as a parenthetical remark, the whole Lagrangian and the full quantum field theory comes in the action. So really as the integral of a Lagrangian. And then if you do Wick rotation, it comes in with a plus sign, such that the kinetic term needs to have a minus sign for suppression. It needs to have the right sign. And quantum electrodynamics, we have minus a quarter F mu nu, if you remember. That minus sign is important. Here we have plus. So is this wrong? Where would the minus come from? Yeah, we're not talking about the Hamiltonian here. That would be a number of steps further. I just want to get the minus sign there in analogy with QED.
Charge.
There is no charge there. This is just a kinetic term. Charge is a coupling. This trace term is the only place that could produce the minus sign. Now, why would it produce a minus sign? Sorry?
Trace of TATB is how you normalize it.
Right. But could this be negative? I mean, usually when these are Hermitian matrices, this is positive.
You have to find them different.
But they're not Hermitian, they're anti-Hermitian. They have an I in them. So you get I squared, and that gives you the minus sign. So you can always choose a tree. In fact, that is this readable? Yeah. TATB is minus delta AB. So you just rescale the fields to get this result. More generally, this is called the Cartan killing metric, but then you can also rescale the fields to get minus delta AB. And the minus is because we're dealing with anti-Hermitian matrices. So as far as the kinetic term is concerned, just n squared minus 1 copies of QED. If you only restrict yourself to the kinetic terms. Okay, I think that was a useful remark just to make. It's something to look not just at formulas, there they are, but what is the, can you read them, can you understand aspects of them? So now, having done this, so such a form, once you've implemented this, is the form from which you would extract the Feynman rules, where all the details must be on the various lines going in and out. But you see how straightforwardly it derives from the general form of the action and the elegant theoretical derivation. So there's a real direct connection to the Feynman rules we derive from here, to the elegant form of the action, which is directly related to the path integral into which it sits. So we can now come to Lagrangian for QCD, where this is really it, except we restrict ourselves to SU3, and these psi's represent quarks, but we must allow for the fact that quarks come in different flavors. So let me write then the action. So QCD for NF quark flavors. I better stick to British spelling, it's also in the text. Lagrangian is the sum from f is 1 to nf of minus psi bar f d slash psi f minus mf plus a quarter the trace of g mu nu. So just hang some label F on things, of course, only on the fermion fields, not on the covariant derivative. That doesn't depend on the quark flavor. I am allowed to choose different masses for the flavors. For each of those choices, of course, I have n copies, n being 3 for QCD. So for NF, you can say, why don't you just write 6? We know of 6 quark flavors. That depends, we'll get to that. Depending on your problem, you might want to describe things less than if you have low energy, there's no point in including the top quark among these flavors. I do want to make one remark on this Lagrangian before we move them more towards diagrams. And the remark is on global symmetries of or rigid symmetries of of the QCD Lagrangian, given the fact that we have multiple flavors. So the relevant remark is that we have projection operators, projectors, PL and PR, where PL is defined as 1 plus gamma 5 over 2, and PR is 1 minus gamma 5 over 2. Have you seen this before? Yeah? There's a gamma 5 squared is 1, and it commutes with all the other gammas. This one is, of course, not a 1, it's a 4-dimensional one. And they have nice properties that PL, PR is 0, so they're orthogonal, and they're idempotent. PL squared is PL, PR squared is PR, and the sum is 1. So then I can write any combination like this as C psi L bar d slash psi L plus psi R bar d slash psi R. When I stick in here PL plus PR, and I stick in here PL plus PR, which is 1 in both cases. But it turns out the cross terms vanish. There is no PL times PR or psi L psi R, thanks to the slash, the gamma mu's in the middle. So from this point of view, it looks like the left-handed components and the right-handed components are separate fields. We can call this Zippo and this elephant. But it's separate fields. And in contrast, the mass term, which does not have a gamma mu inside, in between, that you write as psi L. That does mix the two chiralities. So, from the point of view of chirality, M mixes the two, and the kinetic term does not mix the two. Now, let's assume that the mass is 0 for some flavors. Let's take a couple of flavors and assume that their mass is so small we neglect it. So assume MF is 0 for F is U, D, up to whatever we think is relevant for the problem we would consider. Now then I can easily make an observation which requires hardly any calculation. So if I ignore this and have that, well, let me just write down the kinetic term of the action. So L is then sum over F minus psi bar L d slash psi L minus psi bar R d slash psi R plus the trace of G squared quarter. And these are F's. There's also F label on here. Comma F, comma F, comma F, comma F. So this has let's call it up to number of LF, light flavors. So this has symmetry UL, number of light flavors, UR, number of light flavors. What do I mean by that? So these is U is unitary matrices without determinant 1. They can just be unitary. And what this says is that suppose I have NF, think 2 or 3 light flavors, and this would be U2, and U2, 2 by 2 or 3 by 3 unitary matrices that work not in color space, but that mixes the flavors. So it mixes up and down the strange, but it's not mixed the color inside up or the color inside down or the color inside strange. So I can start mixing up and down independently from mixing the left-handed parts and the right-handed parts, because there's no term that has both of them in. I can make a transformation on the left hand without doing anything here. Therefore, I have the product group. Is this somewhat familiar? I will not go, this is not core of the course. I just wanted to point this out, that QCD Lagrangian has more symmetry than just color. That's a local. The color symmetry is true for every flavor individually. This symmetry mixes the flavors, but in a global way. It's not a local symmetry. There's no gauge field associated with that. So these matrices are constant. Now, this is actually a whole field in and of itself. I think some of you may be working on that too. The nice thing of this is this a symmetry not just of the Lagrangian, but of the physics of the system? And this symmetry, this chiral symmetry, is broken by the QCD ground state. So we assume that QCD has a non-zero condensate, bound states of quarks, a bit like the mass term, and that mixes left and right. So the ground state is something like this, U, L, UR plus UR, UL plus DL, DR, etc. As a condensate, something that binds them in the ground state. The reason we think that is actually because of the consequence of this. If some of you had this in field theory, if not, then maybe you have a first view of it and then can't forget it again. When the Lagrangian has a symmetry, but the ground state breaks it, that's typically a situation of spontaneous symmetry breaking, and that leads to Goldstone bosons. So this gives you Goldstone bosons. Massless excitation of the spectrum as a result of the broken symmetry. That's a whole class in and of itself. The reason I mention it is that if you assume this, and of course we cannot compute this analytically, the same way we cannot compute the proton from the QCD Lagrangian. But if you assume this, Goldstone bosons follow, and what would they be? Well, suppose you only treat up and down as the light, as massless quarks. Then you would have U2 cross U2. And that gives you then three, then basically, and what you can have is that UL and UR can no longer transform independently, but they can transform exactly together. If that happens, this is still a symmetry of the ground state. If L and R happen exactly together, because they're mixed, it's still a symmetry. But you cannot have one rotate differently from the other. So that means that of these two U groups, one still remains and one is broken. So if I transform together, there's still a whole U group there, and U2. But one of the other twos, is actually a linear combination of them, is broken. That means three Goldstone bosons. And these will be actually the pi plus, the pi minus, and the pi zero. So we can explain pions as the Goldstone bosons of the broken global symmetry of the QCD Lagrangian. If you would assume also the strange to be massless, it's a bit heavier than the other two. Then you would have U3, U3. How many Goldstone bosons would I have then? 8, right? Because you're now breaking U3. Never mind the S then. So then you get the pi plus, pi minus, and also the kaons are then Goldstone boson. Now, they're not exactly masses, we know this, right? These have a small mass. They're called pseudo-Goldstone bosons, so it's a small extra symmetry breaking term. But it explains why they're so light. The lightest particles we have in a strong interaction. And this beautiful idea is now still alive, not just for pion physics, but even for beyond the standard model physics. The Higgs is also very light at 120 GeV, and people have thought of ways of making the Higgs a pseudo-Goldstone boson of some bigger symmetry to capitalize on this QCD idea. So the field for this has also a name. You can do perturbation theory with this and set up an effective theory called chiral perturbation theory. Beautiful field in and of itself, but not what we'll address now. But I just wanted to mention it as another symmetry of the QCD Lagrangian. Any questions about this? No? All right. Then I'd like to move to using the QCD Lagrangian to construct Feynman rules, and then we're slowly going to look at diagrammatic things. We already did that a little bit with electrodynamics yesterday with charge conservation. Maybe I'll leave this one. Sorry? Well, we have seen pions, so in that sense, they're seen. In the case of the Higgs mechanism, not then they're eaten by the W's and Z's. You can think of one of the components of W, which you have seen as a Goldstone boson. But also in condensed matter systems, we have seen the spin waves are manifestations of a broken global symmetry, and then you see them. So, in chiral perturbation, just in words, I won't write anything. What you do or to describe the dynamics of the QCD, Lagrangian quarks and gluons, and these pions, because you work at low energy. This is low energy effective theory. You like to have in one theory together the quark and gluon degrees of freedom and the pion and kaon degrees of freedom. And you set up an effective theory for that, and then do perturbation theory with that. And it works quite well for many. Even though it's non-realizable, it works quite well for many problems in low energy QCD. So let me now come to Feynman rules and diagrams in QCD. Now I assume that in your quantum field theory courses you've had some exposure as to how you extract from a Lagrangian or from a path integral the Feynman rules of a theory. Generally speaking, the terms quadratic in the field lead to propagators, the terms cubic and quartic, etc. lead to interactions. And I assume that we can always address this in tutorial if it's not the case. So this is a setup for perturbation theory. And the perturbation theory is, of course, in the QCD coupling G, or rather G squared over 4 pi, which we call alpha S, for the strong fine structure constant, alpha sub S. So I'll just give you some rules and see if you agree with them. So let me begin with the quark propagator. That's also in the notes. So we have here P going on, and then we have here, we need to specify the spinor indices alpha, beta, and also the group indices ij. These are the spinor indices ij, are the SUN, SU3 group indices. I should say, and you see this most of the time in the following, QCD is a theory for SU3. Nevertheless, I will always, almost always write not 3, but n sub c. And to keep it a bit more general and keep track of the color, if you have the number 3, then 3 can come from anything. But if you have n sub c, then you can trace, that was a thing from the color quantum number. At the very end, when I need to put it into a computer program, I can always choose nc as 3. But it's good to keep it as a separate, as a parameter, as long as possible. So what is the propagator? Well, in our conventions, every propagator has this prefactor, 1 over I, 2 pi to the 4th. It's there. And then we have actually the inverse of the quark propagator, which is I think it's I p slash plus m alpha beta. And the QCD color, nothing happens to it, so there's delta ij up here. Now, this is a weird notation, right? 1 over a matrix. It just means the inverse of the matrix. I could easily rewrite this by multiplying with minus ip slash plus m upstairs and downstairs. And then this is 1 over I 2 pi to the 4th delta ij minus ip slash plus m alpha beta p squared plus m squared. The plus m squared is because of the metric choice. For those of you in the know, and you can always think here of a very small imaginary part for making sure that the poles are not exactly on the real axis. And alpha beta, so the conventions are always like a salmon, go upstream. So you start at the end of the charge flow. I'll indicate the charge flow on the line and go back. So you start here and then go back to beta. Okay. That's for the quark propagator. For the gluon propagator, we also must first specify the Lorentz indices, which are not spinor but vector, so mu and nu. And now the color indices, and those would be ij. Well, typically we use Latin letters from the middle of the alphabet for the fundamental representation, and we use letters from the beginning of the alphabet for the adjoint representation. It's a convention. So then you would have AB. That's a good choice. CD would have been fine too. And then the propagator is 1 over I 2 pi to the 4th delta AB, and the momentum going through here is k over k squared. And here is the answer: eta mu nu, the Minkowski metric, minus 1 over lambda squared k nu over k squared. Now, certainly the first term is probably not surprising. This one may be surprising. This is the gauge fixing term. Have you all had gauge fixing in gauge theory? Yeah? If you haven't, then let me know, that we can do a short intermezzo on that. In words, I'll say at least that if you compute the propagator from the inverse of the kinetic term of an action, which is only possible if that kinetic term is invertible. And here it's fine, but for the gauge action, the minus a quarter, this bit, turns out this is not invertible. This 4x4 matrix that you find here has 0 eigenvalues, so you cannot invert it. So what you do is you add a term to the Lagrangian just by hand, such that it is invertible. That seems like well, I can fix anything that way. But you must make sure then that whatever you add does not influence any physics. So it's more of a calculational trick, and that actually is the case. So you add, in fact, a term like minus a half lambda d dot a or d dot w squared. This you add to the Lagrangian, and then you get this extra term. Often then and lambda is for you free to choose. Of course, the first thing you choose, why difficult, I choose lambda as 1, then it's so easy. And I understand that. That is a human instinct. And we'll most of the time do this also. But in practice, if you work on these things, I advise you not to always do that. Because if you keep it in your calculations, you have a very strong check in your calculations. Everyone makes mistakes. And if you find ways of checking your calculation being lambda independence, then that's a very good handle. So many experienced calculators will keep such parameters in for a long time. Okay, that's for the propagators. Then I'll write one 1.5 vertex. So this would be the gluon-quark interaction. Well, let's start writing down labels here. First, the charge flow and the spinor index, alpha and beta. These are Lorentz representations. We need one more, the Lorentz index for the gluon, that's a mu. Then we need to festoon it with color indices. So we'll do I, J, and this should be an adjoint index. And this then is the rule I 2 pi to the 4th. Momentum conserving delta function. So if P1 comes in here, P2 goes in there, and K comes in here. There's P1 plus K minus P2. And the strength is a parameter here, G is minus G. And again, you have to go against the charge flow, also for the color indices, so it's IJ. And we have gamma mu, alpha beta. So basically sits at this vertex sits not just the charge, but also a color generator, a generator of SU3. You see all the indices are accounted for. The key one, and that is also given in one of the problems that you can work on this afternoon, the 3 gluon interaction. So we'll do mu nu rho, and it's always best to go anti-clockwise. So mu nu rho, and then A, B, C. And then you can make them all incoming, K1, K2, K3. And this rule is I 2 pi to the 4th minus IG F ABC. Well, I'll just write one term down. So it is K2 minus K1. Okay, so we start here, then go to the next one, K2 minus K1, with a Lorentz index rho. And then the eta is mu nu plus cyclic, plus 2 cyclic terms. The thing to realize here is, of course, the color structure is fairly easy. That's just the structure constant. That's just the thing in front. This is a bit of a nasty term, 6 terms, with 3 Lorentz indices. There's momenta inside, reflecting that there was a derivative here, right? This derivative leads to momentum in the Feynman rule. So I will not write down the 4 interaction because there are no derivatives. It's just a huge mess in terms of color. But I'll ask, what is the order of this? If I would write down the Feynman rule for the W to the 4th term, what is the coupling constant in front? G squared, indeed, right? So it's often a bit forgotten, but of course for calculations you have to include it. But at least 4 gluons at least, and that doesn't occur too often. So these are the Feynman rules one works with, and I've assumed you've worked a bit before with Feynman rules. So what I'd like to propose is that we now start looking a bit at some QCD reactions. To see how you use the Feynman rules in a very simple way. First of all, later on we look at loop diagrams when divergences come in. This is when QCD really comes into its own. You have to confront that, and it's actually not just difficulties but beautiful insights as well. And I'd certainly like to stress those. Okay, any questions so far on the Feynman rules? It's not particularly deep, it's just mechanical. You have to be careful. I may even have gotten a sign or so wrong, but I won't hold that against you or me. Okay, so we have seen the QCD Lagrangian in its nice symmetric glory. We've then looked at components, and from that we extracted Feynman rules with which we can construct Feynman diagrams and then start computing cross-sections. Now, a very nice and simple cross-section is the so-called Drell-Yan process. Very important reaction in particle physics. It really deserves a bit of discussion. And the process is really the collision of a proton with another proton, or possibly an antiproton, say, and out comes a lepton, an anti-lepton, and other garbage, X. So PP would be, say, the LHC. PP bar would have been the Tevatron in the US. You could also call it proton on a fixed target. Fixed target experiments have been happening. All of that, as long as it's the muon anti-muon or electron anti-electron comes out, or an electron neutrino comes out, we call it Drell-Yan. So the way we look at it cartoonishly is as follows. Here comes a quark, here comes an antiquark, and then out comes, say, a mu plus and a mu minus, for example. And this is then a photon or a Z boson. So we have two quarks colliding, and I'm drawing here also a bit the parton model, right? This is a quark coming out of this proton, the antiquark coming out of the other proton. Those are the ones that collide. The rest of the proton and antiproton just pass through each other. That's what these things signify. And the production of the final state happens in the hard scattering. Now, why is this such an important process? Well, it was related to the discovery. It led to the discovery of the W and the Z in the 1980s at CERN, UA1, UA2, very important experiments where for Z you would have this, for if you would have a W here, you could get a muon and a mu neutrino coming out, and that was a sign of monojets. And so anyway, that reaction led to that discovery, but also discovery of J psi and the upsilon. These are the CC bar and BB bar bound states. And those were very important. J psi was a major discovery that really cemented a lot of thoughts into, made them solid. The fact that there was a second family, that there was a partner, we knew up, down, strange, but that there really was charm was a major discovery. And then the bottom quark signaled the presence of a whole third generation of fermions. So also here, major importance for the Drell-Yan process. And very recently, discovery of the Higgs. The Higgs very much looks like this, except now we have gluon to some effective vertex to the Higgs. It's a bit like Drell-Yan's gluons, but you have a gluon coming out of the proton and a gluon then producing a Higgs. So this type of process has been very important, and it is worthwhile to look a little bit at it. The thing to also observe is that I'm telling you this is important for QCD. This is a course in QCD after all, but it's kind of funny that if you look at this diagram, it's all QED, or like the weak. So if it's a photon, this is a EM vertex and EM vertex. So at lowest order, there's nothing QCD about it at all. All it does is it tells you a bit about the presence of quarks and antiquarks and protons and antiprotons. So it has that. But once you get higher orders, this is very important for QCD. It functions for us a bit as a theoretical laboratory. That's a bit of a contradiction in terms, perhaps. But when you have new ideas about perturbation theory, about loop techniques, often the first place you try it out is Lagrangian. And certainly I do, because it is fairly simple, but exhibits many of the key features that you're looking for. So let's work a bit with that and compute this cross-section. Now to compute it, the picture indicates more or less the procedure. This part, the central, the hard scattering, we can compute using QED. And this bit we compute using the ideas of the Parton model. That's the way we translate, we match from the hadron to the Parton level. So we have then let me write it again in a bit of detail here. So we have here the hard scattering. So I'll first draw the charge flow on the lines, and then the momenta. This is coming in, this is coming out. And you know that if the charge flow and the momentum flow in the same direction, it's a particle, and if it's in the opposite direction, it's an antiparticle. So this would be a quark, this would be the antiquark, and this would be the lepton, say, and the antilepton. And this we call momentum P1, and this momentum P2, and this Q1 and Q2. And this is momentum big Q, or just Q. Okay. Have you done these calculations all before? Some? A little bit? Is it useful to do, or should I skip it completely? Useful to do. Okay. Now, in the Parton model, we're going to I'll first describe how you use the Parton model and then compute what we need to compute. So in the Parton model, you say that this momentum P1 is really a momentum fraction psi1 times the proton momentum P1, and P2 is psi2 P2. And then once we compute it, we have to combine it with the PDFs. We first define some kinematical things. So we have the variable s hat defined as minus P1 plus P2 squared. The typical Mandelstam S. The hat is on it because it's at the Parton level. Usually without the hat, it is at the hadron level. So regular S is minus big P1 plus big P2 squared, by definition. So this is equal to psi1 times psi2 times regular S. You have to realize here that P1 squared is 0 and P2 squared is 0 because they're massless fermions. And then you see it. We also assume that big P1 squared and big P2 squared is 0. P1 squared is like the proton mass squared. The LHC has a collision energy 7 times larger than that, 7,000 times larger than that, so we ignore the proton mass. Okay, so P1 squared is 0 here and also here and here. Please interrupt if I'm saying things that are not clear. We also define a Q squared, which is just Q1 plus Q2 squared, which is smaller than 0 in our metric. S hat is larger than 0, thanks to this minus sign. And this is really just because it is minus plus 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 metric we use. This is smaller than 0, so we often define big Q squared to be minus Q squared to be larger than 0. These are the typical variables you introduce. Okay. Now, suppose I've computed the cross-section for this diagram. I'll do it in a moment. Actually, I'll do it after the break. Then, how do you then implement it in the Parton model? So, well, let me give you the formula. So, the cross-section for P collisions for Drell-Yan and it's the lowest order, so I'll write a 0 here, meaning no QCD corrections yet. Differential in Q squared. So Q squared is the invariant mass of this final state, right? It's the sum of the two final state momenta squared. Can be written as the sum over I and J. Let me just write the formula and then discuss it. And this would be from xi1 min, xi2 min. So this is really the instruction of the Parton model we write here. Let's go through the formula. It reflects that cartoon picture. So if you want to compute the differential cross-section for the proton-proton collision in the invariant mass, so make a histogram in the invariant mass of these two leptons, which we cannot compute from first principles, then here's what the Parton model says. Well, first compute the partonic cross-section, this bit, square the amplitude, do the integral, we'll do that. That gives you the partonic cross-section, that we can compute. But it's been computed with incoming momenta that have fractions of the proton momenta. Now multiply that, convolute that with the Parton distribution functions for parton I coming out of the proton and parton J out of the other one. In this case, I and J are quark, anti-quark, up, anti-up, anti-up, down, anti-down, etc. And these things you must download from the web. That's better than computing over first principles. You just multiply this together, and you typically do that on a computer. And then you integrate over all allowed momentum fractions. There's no way you can restrict that. You must integrate over what you cannot restrict. So you integrate from some lower value up to the maximum value that the size can have, and that's never more than 1. The particle cannot make more momentum out of the proton than the proton has. And you sum over all contributing initial state parton types. Up, anti-up, down, anti-down, etc. So what you typically do then is you compute this. Analytically is a formula. In these days when you do difficult stuff, also this is a computer program. You download, you have a package for these, you combine that, and then you do the numerical integral also on the computer with the parton momentum fraction. Outcomes a prediction. Yeah. So that's how you use the Parton model. If someone gives you the Parton distribution functions, it's a very simple thing to do. It takes a few lines.
Sorry, what is the Parton distribution analytically?
This one. It's the thing with the IJ means the Parton types, quarks, gluons. In this case, quark, anti-quark. That we can compute. I can compute with quarks and gluons thanks to the Feynman rules I just derived, but I cannot compute with protons. Right? The transition from the parton, the quark gluon level, to the protons is through these PDFs.
So,
Yeah.
As mathematics is concerned, can we use direct product or convolution between two PDFs?
Can what? Can
Convolution or product.
Yeah.
Between two.
In this case, well, here it's a product. If you often, for certain cases, you write it, it looks like a convolution.
Okay.
But this is the instruction.
Okay. Yeah. So
You could take this formula and program it.
Yeah. So my doubt is that when to use convolution and when to use product.
So this is the correct formula. So there are cases, I should maybe do that here, when it turns out to become a convolution for certain observables, like deep elastic scattering.
We need some Millian transform to use.
That's something, then that's a step further than that. But this is just a basic instruction.
Okay.
And you don't need a Mellon transform. It's sometimes useful, but you don't need it. Yeah. So is this idea clear? So again, this is a brief return to the Parton model in order to link QCD, the theory of quarks and gluons, to actual high energy scattering. What I will then do in the next lecture is to compute this bit, which involves squaring this diagram, summing over spins, doing the phase space integral. It's a bit of technology, but maybe worthwhile going over, I think. Yeah, just to see how it goes. And then we have a prediction for that particular cross section. I will also later in the course come back a little bit on these guys, these PDFs. Fortunately, this is an overloaded concept. We all know it as something that you look at documents from, but it's also for people in high-energy physics part of the distribution function. Sorry about that. You have to see from the context which is which. So I told you that these are downloaded, and that's certainly true. There are some very nice packages made by various groups, and the groups are something the CT10, you have the MSTW, you have the NN PDF, you have the ABM group, you have a number of others. All these initials, almost all the initials refer to people. Martin, Sterling, Thorne, and Thorne and Wyatt, Watts. CT for the CTEC actually. This is Aljechin, Blumlein, Moch. This is different. This is neural network PDF. So they really apply neural network technology. It's really quite exciting to infer as a self-learning system from the data, the PDFs. And we'll get to that later in the course. I do want to address this a bit. The reason why I address this is that you see the quality of the prediction is as good as the weakest link. So if I compute such thing to 15 orders in perturbation theory to part per million precision, I can't, but suppose I could. Then, and if this is only known to 10%, why am I bothering? So all things must be improved. And what these groups do is very impressive to make the best possible predictions. Not just for what they are, but including error estimates. There's sort of a recent development the last 5 years that these packages are produced including errors, including uncertainties. Because your prediction when you make it must not just be a line or a number, but must have an uncertainty. We need to be sure that our prediction agrees or not with the data, and that means the data have an uncertainty, the theory has as well. So this is now the big thing, and this is very impressive technology that goes in here. In the end, it's downloadable. Okay, so after the break, I will compute this bit. Are there any questions?
What are those, why do you have the 0 thing?
Oh, the 0 here? I just mean lowest order in QCD. It's a bit, I could just keep in mind that we could and we will look at higher order corrections to this. But 0 is the lowest order. There is no QCD correction here, that's right. Yeah. The only QCD sort of sits in these phi's. Not perturbative QCD, that's right. Yeah. Okay, is this a bit clear? The idea and if you, by the way, still a bit unsure about the motivation for this formula. This was the story of Feynman with the pancake, etc. He used all that motivation to set up such a formula. So if you're unsure, discuss it with each other or with me. I'm happy to explain it again. Okay. All right. Let's have a break for half an hour. Okay.